Great. Our next speaker is Professor Sungjay Lee. The title of his talk is Monster Anatomy.
Right, thank you. I'd like to begin by thanking the organizers for this opportunity to give a talk at this wonderful workshop. And today, my title of my talk is Monster Anatomy. I wouldn't say this talk will be a physics talk. It's more like a mathematical talk. So please enjoy it. This talk is based on two papers in collaboration with Sungjay, who was a postdoc in KIAS, recently moved to Oxford, and Kim Young-Lee sitting somewhere in this room there, and Jeff Harvey, Chicago, and Brandon Bacon, Stanford. So let me first start with some remarkable observations made by McKay and Thompson. So they found that there is an interesting relation between the modular object and the monster group N. So here, the modular object is considered the J function, which is given by this expression, where E4 and E are Eisenstein series. They are modular form of weight 4 and weight 6. And their two expansions are given by this expression. Since we know how they transform on the modular transformations, it's easy to see that J function is invariant on the exotic transformations, but under which this tau parameter will transform into these expressions, where ABC design feasibility and satisfying this relation. The reasons why physicists get interested in this J function is that actually this J function arises as a partition function of some continuum field theory. Central side is 24. And this continuum field theory was conjectured to describe the quantum theory gravity, pure gravity in a free space by Witten late 2007 or something. And here, monster group is the largest sporadic finite simple group, which has a tremendous order. As you can see, it's roughly 10 to the 54. It's a huge number. And they found that when they expand this J function in powers of Q, so Q is defined as this. Each coefficient in this coefficient can be expressed as a sum of the dimension of irreducible representation of this monster. For instance, this number 19, 68, 84 can be decomposed into 1 and 19, 68, 83. And this number also can be decomposed as 1, 19, 68, 83, 21, 29, 68, 76. All these numbers are the dimensions of the irreducible representation of this monster group. And there is a heuristic derivation why this there is before that this phenomenon goes under the name of this monster moonshine, and those three gentlemen provide a heuristic derivation of this monster moonshine from explicit constructions of the secret 24 CFTs. This CFT is basically compact Boson theory defined on the Leach lattice. The reason why they choose this Leach lattice is that this lattice has some isometry, which is the monster group. So the goal of today's talk is to generalize this moonshine phenomena for a different sporadic group. In other words, we need to find a relation between a modular object other than the J function we discussed and the sporadic group other than the monster group. Actually, this is not a trivial problem. Only recently by Eguchi Oguri Tachikawa, they found another example of this moonshine phenomena, which is now known as the Matthew moonshine. So there, the modular object was chosen as elliptic Venus on the case 3 surface, and the sporadic group turns out to be Matthew 24. So before going to the next things, let me first show you the diagram of the 26 sporadic simple group we have. So here M represents the monster group, B is called the baby monster, and HM is known as the Hanada Norton, Thompson, Conway, Fisher, and Jampo, and so on and so forth. And this diagram shows the subportion relation between two different sporadic groups, such as the baby monster group is a subgroup of the monster group. Fisher is the subgroup of the monster. However, coordinate 2 and coordinate 3, coordinate 3 is not a subgroup of coordinate 2, although both of them are subgroup of coordinate 1. So these are the complete list of known sporadic finite simple group. And from this table, you can see the order of these 26 finite simple group. Sporadic finite simple group. As I told you, the monster group has roughly given by 10 to the 54, and you can see there that all of them has 3 numerous orders. So we'd like to find some moonshine phenomena for these 65 sporadic finite simple groups. So to do that, let me first briefly review what the rational conformal field theory is. So as all of you know very well, any two-dimensional conformal field theory has 2 copies of infinite dimensional symmetry algebra that's moving via through algebra, satisfying these commutation relations. And here we have some C number, which is called the central charge. So in principle, we have 2 different C number, C left and C right. But today we're going to focus on parity preserving conformal field theories, meaning that C left is equal to C right. And since two-dimensional conformal field theory has this symmetry algebra, we can decompose this Hilbert space into representation of the symmetry algebra. 2 copies of the algebras, which is given by this expression. So each representation of the algebra can be characterized by this number h, which is called the conformal weight eigenvalues of L0. And DHA are just left-moving representations, left-moving algebra representations. This is the right-moving representations. And DHH bar will count how many times this representation will appear in the Hilbert space of given conformal field theories. Then let me discuss about the torus partition functions. So for that, we will consider some conformal field theories compactifying on the circles at temperature given by 1/2 τ2. So as all of you know very well, it is defined as follows. We perform the trace over Hilbert space of the conformal field theory compactifying on the circles. The H is the Hamiltonian, J is the momentum charge along the circle, which is here to define on. And we introduce some chemical potential associated with it. And using these relations, we can rewrite this expression into the following form. And as I told you, Hilbert space can be expressed in this way. So we can rewrite this expression into the following form. So each trace is called a zero characters. Any question? So when a central charge is greater than 1, it is known that there are 2 different types of conformal characters. One is the vacuum character. The other is the Virasoro character for the primaries, whose conformal weight is given by h. So partition function can be written in this way. And we can argue that this torus partition function has to be invariant under SL2G. As it is well known that this SL2G can be generated by 2 elements, T and S. But in the invariance under the T simply requires that this conformal field theory should carry only integer spin state. However, the invariance under the S transformation will give you very strong constraint on the spectrum DHH bar. And this consistent condition goes under the name of the modular bootstrap equation. When central charge is less than 1, this consistency condition can be solved analytically thanks to the Zhang-Wei curve. And as a consequence, we can classify 4 possible conformal field theory with less than C, which are known as the minimum model. The central charge is given by these expressions. An interesting feature of this minimum model is that this theory has only finite numbers of primaries. However, when the central charge is greater than 1, one consequence of this consistent condition is that any unitary conformal field theory with central charge greater than 1 must have infinite numbers of primaries. And that makes this problem, solving this consistent condition analytically, extremely difficult. But today, I'm going to discuss a special type of conformal field theories, which are somewhere between this minimum model and generic conformal field theories with the C greater than 1, which is known as the rational conformal field theories. The rational conformal field theory is a special type of conformal field theory, which has a finite number of conformal primaries. Since it has a finite number of conformal conformal primaries, the partition function can be written as the following. But it sounds a little bit wrong, because as I told you in the previous slide, you need some infinite numbers of pairs of primaries. But this rational conformal field theories, even when their central chart is greater than 1, has a finite numbers of conformal primaries. The way to circumvent this is that this conformal primary is a primary with respect to some bigger symmetry algebra, which contains the Virasoro algebra as a subalgebra. And from this expression, we call this Fi as the conformal character. And these two gentlemen, Anderson and Moore, have shown that when the partition functions take the following form, the finite sum rather than infinite sum, both central chart and the conformal weight have to be rational numbers. That's the reasons why this kind of CFT are called the rational conformal field theories. And one prominent example of this rational conformal field theory is the monster conformal field theories, what I introduced in the beginning of the talk. The partition function is written as this simple form, which means that this conformal field theory is single character. There's only one primary, vacuum, character rational conformal field theories, whose character is given by J function. Again, when you decompose or expand this J function in terms of the Virasoro characters, you can see that infinite numbers of Virasoro characters are involved in these decompositions. And each coefficient turns out to be dimension of the irreducible representations of the monster finite sporadic finite. And from this expression, you can also see that this set of conformal characters should transform into themselves under modular transformations. Otherwise, there is no way to satisfy the modular invariance of the function. Which means that under T and S transformations, this conformal character will transform into this way, where matrix T and S should satisfy the Lem relations. This means that these conformal characters are nothing but the vector valued modular functions. And since the conformal characters are vector valued modular functions, they must be a solution to this so-called modular linear differential equations. Due to the lack of time, I will skip all the details about this modular linear differential equation. Important thing is that there's a very special type of linear differential equation, which is invariant on the SH2J transformations. Since this linear differential equation is invariant, the solution, the set of independent solutions to this modular linear differential equation also must transform into themselves. In other words, the solution has to be vector valued modular functions. That's the reasons why conformal characters have to be a solution to these modular linear differential equations. And recently, Mookie and his collaborators utilized these modular linear differential equations to classify all possible rational conformal field theory, just like the classification of the minima model done by Sungjay. So let me present a well-known example. Ising model. It's very simple theories. It's one famous rational conformal field theories. In this case, Ising model has three primaries, identity operators, and two primaries of conformal weight half and 1/16, and their characters are given by this expression. Indeed, you can show that these characters are solution to this particular modular linear differential equations. And from this sort of expressions, you can easily read off those transformation matrices S and T. And from that, you can easily write down the modular invariant partition function, which is given by these expressions. All right, so I think we are ready to discuss attack this problem, generalizing the moonshine phenomena for different sporadic groups. So as I told you, to do that, we first need to find the relations between a modular object other than J functions. And today, we will take this conformal characters of rational conformal field theories as a modular object, which will exhibit this moonshine phenomena for other sporadic groups. So in other words, we will consider vector valued modular functions today. And before attacking this problem, let me add one more thing to this test of characters today's talk, which is the bilinear relations. Recently, Hampakura and Yuki observed that Fi, the conformal character, is a certain rational conformal field theory with the central charge C, and F tilde I, which are characters of the dual rational conformal field theory with central charge 24 minus this. These two can combine to satisfy some intriguing relations giving the modular invariance, which is the J function. And remember that this J function is nothing but the conformal character of the monster conformal field theories. And this bilinear relation has two implications. The first implication is that the Virasoro generator of this monster CFT can split into two pieces, two different Virasoro generators, denoted by L0 and L0 tilde. The L0 is the Virasoro generator of rational conformal field theory with the central charge C, and the rest, L0 tilde, can be identified as the Virasoro generator of the dual rational conformal field theories with the central charge 24 minus. And the second implication is that the Hilbert space of the monster conformal field theories can be written as the following form, where VA and VA tilde are the representation of the dual rational conformal field theories with central charge C, and this one is the representation of this dual rational conformal field theory with the central charge 24 minus 6. When these two relations are hold, you can show that this conformal character of the monster conformal field theories can be rewritten into these expressions, and each trace is nothing but the conformal characters of either rational conformal field theory we start with, or the dual rational conformal field theories, meaning that Fi, this one can be identified as Fi, this one can be written as Fi tilde.
So the number of your primaries of dual conformal theory is always the same? As
has to be same. Otherwise, there's no way.
And the J tau is a modular invariant function.
It's a modular invariant function.
So this combination should be modular invariant. Although
yeah.
F and F
Fi is
are
not really
covariant.
vector. Yeah.
They are covariant.
That means the way how it Fi and Fi tilde transform on the SL2J have to be the same.
So for any conformal theory, there is a dual conformal theory?
No. If it's maybe you can find some F tilde I, but when you expand in parts of Q of Fi, you wouldn't get the integer coefficient. So there is a very special type of conformal field theory, rational conformal field theories, that explain this bilinear relations.
So here the small n and c are specific value, or
Here everything's arbitrary.
arbitrary?
But there's only a few numbers which satisfy this relation. Yeah.
Not unique. Yeah.
There's not many examples.
Okay.
Yeah, satisfying this relation.
And do you know the algebra of this character, this extended character?
No. There is some mathematicians, for some examples, some mathematicians work out the so-called vortex operator algebras, which I never understand. But we found much more than that. Or many more examples. But mathematicians didn't work out. Any other questions? So to avoid being abstract, let me work out one simple explicit example. So let me first take the Ising model as one of these rational conformal field theories, and the other rational conformal field theory contains some conformal characters which are solution to this particular modular linear differential equations. So when you solve it, the three independent solutions are given by these expressions. From that, you can see that this pure rational conformal field theories, which has these three independent conformal characters. The central charge of it is given by 24 minus C. C is half because the Ising model central charge is half. And it contains three primaries. One is vacuum, of course, and the other one is 3 half and 31/16 from these expressions. And since we know explicit expression for Ising model characters, chi 0, chi epsilon, chi sigma, and f tilde 0, f tilde epsilon, f tilde sigma, we can compute this one. Then you can explicitly show that this expression will give you J functions. So they satisfy this bilinear relation.
But what is that conformity theory?
You are
So you
asking
should
about,
have, if C is bigger than 1,
yeah,
so you should have the extended algebra.
yeah.
So what are they?
Good question, I don't know. Some mathematicians work out this.
So far it's just
algebra.
functional.
Yeah, it's a functional analysis. But the good thing is that from the transformation matrix of Ising model, you can read up the transformation matrix on the SFT of the dual rational conformal field theories, and you can compute the fusion algebra. Everything's well defined. So we believe that there is some consistent rational conformal field theory having this conformal.
So you check that.
Yeah.
For example, you know the modular symmetric property.
Yeah.
So you can check the Berlin formula.
Using the Berlin formula, you can compute the fusion algebra, which I skipped in this talk.
What about Z2 symmetry?
Sorry?
Z2 symmetry.
Sorry?
Z2 symmetry.
Z2.
Z2 symmetry or Ising model.
I will talk about that later in this talk. Yeah. The surprising is when you look at these numbers, which appears in this Q expansion of this conformal characters of the dual rational conformal field theories. The lowest order quotients are dimension of the irreducible representations, double covering of the baby monster group, not the monster group, baby monster group, which was the subgroup of the monster, one of the sporadic group, the second largest sporadic finite group, and other coefficients such as 96 to 56, and this number 11, 43, 7, 45, and so on. All these coefficients can be decomposed into the dimension of the irreducible representation of this baby monster group. So that strongly suggests that this dual rational conformal field theories can exhibit the moonshine phenomena for this baby monster group. In fact, actually we can do much better than this. There is a certain way to explain why this dual rational conformal field theories should have this baby monster group as a symmetry. To do that, let me first remind you that this Ising model has G2 symmetry, some of you asked. So under this G2 symmetries, identity operator's energy field are invariant, but the spin field will flip a sign. And then we will consider, we'll replace this Ising model characters by their G2 twined characters in this bilinear rotation. Here the G2 twined characters are nothing but, can be defined as this way. So before, we didn't put anything here inside the trace. So we get conformal Ising model characters and conformal characters for the dual rational conformal field theories. But this time, let me insert something here. It is a non-trivial element. Non-trivial element of the G2 symmetry of the Ising models inside the trace here. Since we know how this conformal primaries of our Ising model will transform on the G2, we can easily compute these quantities. Identity energy field is invariant, so we will get chi 0 and chi epsilon. However, the spin field will flip the sign, so instead of the plus chi sigma, we obtain minus chi sigma. So let me consider this quantity. This one will just give you the conformal character, the dual rational conformal field theory as before. And since we know explicit expression for all of this, we can easily compute this expression, which will give you this one. And surprisingly, this expression exactly agrees with, up to very high order, with the so-called Mackay-Thompson series of 2A conjugacy class of the monster group. So let me explain first. So here 2A means there is a conjugacy classes of finite group. There is something conjugacy class labeled by 2A. 2A means there is any element of 2A's conjugacy class. When you square it, you get identity. So that 2 means it's degree 2. And Mackay-Thompson series means inside this trace, you will insert this element. And then there is a way to compute this this twined characters. Mathematician already worked out, and that expression exactly agrees with this one. So what does that mean? So on the left hand side we have this, on the right hand side we have this. Which means that this monster group element, which belongs to a certain conjugacy class 2A, can reduce to G2 element of the Ising model. And this element of monster group will act trivially on the Hilbert space of this dual rational conformal space. That means the whole monster group cannot be realized as a symmetry of the dual rational conformal field theory, since there is a subgroup of monster group which will not act will act trivially on the Hilbert space of the dual rational conformal field theories. Only subgroup of the monster group will survive as a symmetry group. And that thing is nothing but the centralizer of this 2A conjugacy class of the monster group. And so interestingly, this centralizer of this particular conjugacy class happen to be identical to the baby monster. So that explains why the rational conformal field theories dual to this Ising model will exhibit the moonshine phenomena for this baby monster. Almost, I used almost 5 minutes. Yeah. 2 minutes. So we can play this game again and again and again. So for instance, let me try to find out the rational conformal field theories which can exhibit the moonshine phenomena for this Fisher 24. Here, all you need to do, you first need to notice that this is a centralizer of the 3A conjugacy class of the monster group. The 3A means any element of this conjugacy class when you consider this G to the cube, then you will get this identity of particles. So first thing you have to do is to find some rational conformal field theories which has G3 discrete symmetries this time. And then try to find dual rational conformal field theories whose conformal characters and the characters of this rational conformal field theory having G3 symmetries can satisfy the bilinear relations. Then the dual rational conformal field theories are expected to exhibit this moonshine phenomena of the central lines of the 3A.
So for SU3 level 1, we do have a dual one.
SU3.
SU3 level 1.
Okay.
Do you have a dual?
I would expect it would be dual, but I'm not quite sure whether it will exhibit this moonshine phenomena. But here, I mean, in order to get this Fisher 24, we consider some parafermion theories, because parafermion theory has discrete symmetry group ZK. So we just insert K equal to 3 and try to find the dual rational conformal field theory. Then dual conformal theory has these conformal characters, and as we expect, all these numbers can be expressed as the sum of the dimension of this Fisher 24 monster as a sporadic finite group. So you can play this game again and again and again. This is the conclusion. So here is tables. We found many examples exhibiting this moonshine phenomena for many interesting sporadic finite groups, but still you can see there are many blanks in these tables. And hopefully I will report some further progress along this direction next year. Thank you.
Thank you very much. Are there other questions or comments? For the Ising example, so for the dual rational CFT, the third operator might also have might also be Z2 order.
Oh yes.
Other questions or comments?
Maybe I'm not sure it's really the question, but if my discrete symmetry is anomalous,
What do you mean by anomalous?
no, you cannot gauge it.
Yeah.
Also anomaly.
Okay.
Then is it doable for?
So you are saying that there is no such a symmetry that one will get for dual
I'm
rational.
not sure. I'm just curious.
Yeah, I'm not sure what to say. Sorry.
Other questions or comments? If not, let's thank the speaker again. Our next speaker is Professor Fenli Li. The title of the talk is Weak Cosmic Censorship Conjecture, Proof and